Welcome. In this video I'll discuss in more detail conservation properties of numerical methods, and in particular two different kinds of ways that quantities can be conserved. So one is when there are direct quantities being evolved for things like density, for example, and this is where you have you're directly evolving something that you want to be conserved. So examples say are things like density, momentum, and sometimes energy in some systems where it's easy to write down the energy equation. And to conserve these quantities, it's enough to write the equations in terms of fluxes through cells. So if we can write our equation in the form of a conservation law, so similar to the density equation, so it has a time derivative of some quantity f as the divergence of a flux, called capital F, and a source S. So this is some kind of external source. This is a flux, and this is the evolving quantity. So for example, F is rho, so mass density, for example. Then the flux is just rho times the velocity u, and then S might be an external ionization source or recombination, some external source of particles. The point is that these divergences can be written by integrating over cells. They can be written as surface fluxes. So you can essentially integrate this equation over a volume. And so we can write down, so we have d by dt of the integral of f dv, where v here is the volume of the cell, and then we have the integral of this divergence of the flux f, and also integrated over v, and this of course is just the surface integral of f dot ds. And so by writing this divergence in terms of flows through a surface in this kind of form, we can make sure that this equation is followed, and that the density, for example, is conserved. And so the way this appears in a simulation is you might have a set of cells, for example here. So this is like a one-dimensional simulation. We divide up space into cells. So this would be the x direction here. We have cell centers like this. So this would be like cell center j plus 1, for example. And here we have j minus 1, just like a numbering for each cell. And what we're going to do is to evolve or solve this equation. We basically solve either the average of f inside each cell, or the finite difference way is you solve f on each cell center. In one dimensions with uniform grid spacing, it doesn't matter which you do, you end up with the same equation. But formally, it can be easiest to think about it in terms of evolving essentially the integral over this volume, and then the integral over the volume of this is just the surface fluxes, and so you're working out the fluxes through these surfaces here. So this would be like f at j plus a half, and this is f at j minus a half. So it's halfway between j minus 1 and j. And this is f plus a half, so it's halfway between these two. And so we write down the change to the equation, so df by dt at grid cell j. We write down in terms of the difference between the flux going in and the flux going out. So a positive flux is going from left to right. So this is f j minus a half. So this flux is increasing the density in here, and flux going out this way is decreasing the density inside. And then we divide essentially by the volume of the cell, delta v. And this ends up, because we're multiplying by the area, so this is like y So f has a factor of y, so f here would be, so f j plus a half, for example, is rho at j plus a half times u j plus a half times the area of the surface. So it's the total flux through the surface, because we're doing a surface integral around the outside of this cell. So it'd be like delta y. And then the volume in this case, so delta v would be just delta x times delta y, be basically the volume of this cell here. And so because this cancels out the delta y's in these factors, and the delta y here cancels out, and you just end up with a delta x, as you would do for a finite difference formula. So this is the same as a finite difference formula. The point of writing it in this form is that now we can change what these fluxes are. Because if you write down the equation for fj minus 1, for example, so you write down the equation for what f is in this cell here, it has the same form, except we now use these fluxes again. So we have j minus minus 3 over 2 minus f j minus a half, for example, for delta v. This is the volume of the j minus 1 cell. And so this flux here, this is this flux on this boundary here. So the flux between j minus 1 and j, we calculate this once, and then reuse it in this formula and in that formula. And then now when we add up, integrate over the whole domain, so we add up what's going in and out of every cell, these terms cancel out. And so we calculate precisely what's going from this cell to that cell, and whatever we remove from this cell, we add to that cell. And so you ensure that the total is always conserved, at least to within machine precision. So there'll always be some numerical round off, but it will be typically very small. And so if we design a numerical scheme, you can make some approximations when you calculate this f, but it doesn't affect the conservation, because whatever this f is the same in both terms, both equations. And so by writing in this form, you guarantee conservation. So here, so if you write your equations in this form in terms of fluxes through cell faces, then you can make approximations to f, and you still guarantee that the total integral over the domain is conserved. And this is not necessarily the case if you write down a standard finite difference formula, particularly if the size of the cells is changing. So if this either the width this way or the volume of the cell is changing, then if you write down standard finite difference formulas, there's an error in the fluxes, and when you calculate the flux in this cell, it's not necessarily the same as the flux in that cell. So typically you'll find an error in the conservation properties. So this form is very useful for things like conservation of mass or momentum. And this is applied in things like MHD. And the point is to write all the equations in this conservation form. So you write down that you have d by dt. You can choose which variables to evolve, and the integrals of these variables will be conserved. And so you write down the mass density, and so the integral of the mass will be conserved. You write down the momentum, and you write down the total energy, W, which includes electromagnetic energy and the thermal energies. And then ideal MHD can be written in this form. So we have the conservation of mass, so rho plus divergence of rho u, and I'm going to put an equals 0 on this side when we've got a bit more space. Momentum, we've seen before, is just rho uu is the advection term, and then we have the pressure, so grad p, and the magnetic pressure, and that's times the identity matrix here. So when you take the divergence, you just get the gradient of p and the gradient of b over, so b squared over 2 v naught. And you have the energy terms, so there's the the advection of energy, so rho u squared over 2 is of course the kinetic energy. We have the thermal energy, so it's gamma minus 1 times the pressure, so that's the internal energy, and this is advected by the velocity u. And then we have the pointing vector, so the electromagnetic energy as well. So these are divergences of the fluxes of density, momentum, and energy. And if there are no sources, then the right hand side is 0. And so this is ideal MHD in conservation form. And so since everything is written in terms of a divergence, we can use these same methods and just work out essentially fluxes of all these quantities on cell boundaries. And so we can ensure that that these integrals are conserved. So you can ensure that the integrals of all these three quantities over the volume is constant, providing there's no external fluxes through the boundaries. Because of course at the outer boundaries of the domain, you can still have fluxes through those boundaries if the boundary conditions allow it. Okay, so that's directly conserved quantities where we're evolving the quantities we want to conserve, but there can be other things that we also want to conserve, which are not being evolved here. An example is entropy for this system, but in more complicated systems it can be very hard to evolve the actual energy. And so the energy may be conserved between multiple equations. So we might have an equation for the internal energy, and we might have a separate equation for the electromagnetic energy, for example. And together these have to conserve energy. And so there might be relationships between different equations which together conserve energy. I'm going to show an example of this. So these are indirectly conserved quantities. And these typically require some kind of an analytic relationship to be obeyed, typically something involving integrating divergences and gradients, some kind of partial integration. So there's something which involves multiple equations and some kind of integral or differential relationship between them. So as an example, I'll show you what I mean. You can look at a simple example of a sound wave, a very simplified form. So if you have a pressure equation, for example, and here we have some kind of compression. So I've assumed sort of gamma is 1 here just to keep the maths easier. So this is a compression with a velocity u, and then we have a du by dt is just driven by the gradient of pressure. So I'm assuming the mass density is constant, it's just 1. So this is a simple equation for a sound wave. So here this supports compression, so compressional sound waves, and of course the sound wave speed just depends on the square root of the pressure, because our mass density is just set to 1. And so we can ask what the conserved quantity is here. So so expect that the pressure is going to form part of that. So pressure is internal energy, and so this usually either with some constant forms part of the conserved energy, and then this is some kind of a kinetic energy. And so usually the way to go with this is to take a dot product with u. So to work out u dot du by dt. So trying to get u squared in here. So you have a u dot grad p. Now this part here you can just simplify. This is d by dt of a half u squared. So that's forming the kinetic energy, and then you can see we've got this relationship here. So u dot grad p, and then here we have a p divergence of u, and these are related to each other. So you can write down that the divergence of p times u is of course just p times gradient of divergence of u here, so that's this term, plus also u dot grad p, which is that one. And so you can write down that this minus u dot grad p. We can write down as here. So this is minus u dot grad p is equal to p times divergence of u minus the divergence of pu. And so we have this equation just stays as it is. So we have dp by dt is minus p times divergence of u, and we have d by dt of the kinetic energy, so half u squared, is p times divergence of u minus divergence of pu. So you see clearly these terms here are the same and they cancel each other. So there's a transfer of energy between kinetic energy and the pressure, which is this quantity here, so p times divergence of u, and then there is this extra term here. So if we integrate over the volume, so this will disappear except for boundary terms. So the integral over the whole domain, omega, of p plus a half u squared. So these two terms cancel. So that's just the integral of minus divergence of pu over the whole domain, which just becomes so minus the integral, loop integral over the boundary of the domain of rho u dot ds, the surface. So this means that this is the conserved quantity. So conserved quantity, which is essentially the energy, so the internal energy and the kinetic energy, and then these rho u dot ds, this is the fluxes of energy through the boundary. So the point is that this system has a conserved energy, so it's p plus a half u squared is conserved, but this is not a quantity that we're evolving. So we're evolving p and we're evolving u, but we're not evolving p plus a half u squared. And so there's no guarantee that if we solve this equation using various finite difference or finite volume or any other numerical method, there's no guarantee that the energy will be conserved. And so what we've noticed is that the conservation of energy depends on this quantity here, on this relationship. And so as long as this relationship holds, we can ensure that our energy is conserved, because in our equations we have this divergence, so p times this divergence of u, and we have this gradient operator, and so we need to write down our numerical method such that the divergence operators and the gradient operators obey this equation. So the kind of discrete form of this equation, and this is called a summation by parts scheme, which is the numerical counterpart to integration by parts. And so you basically choose your gradient operator and you choose your divergence operator so that they have this relationship here. And so you have to choose your divergence operators and gradient operators so that they obey this relationship. Typically, if you have nonlinear, say limiter schemes, then they don't obey these relationships, and so that can break the conservation of energy. And so for these kind of terms, you can use things like central differencing methods. And so for some codes I've been involved in, it can be useful to split the terms into different cases. So some of them where we're evolving the quantity directly, so say conservation of mass, you can treat as fluxes through cells. Other quantities like energy, which are being conserved indirectly, like in this case, you can carefully choose your operators so that they obey these integral relationships. And the terms to look up for doing this are things like summation by parts. If you're interested in more work and literature on this area. Or SBP, so summation by parts, and it's the finite, so numerical equivalent of integration by parts.